Now we've constructed a simple classical example of an electromagnetic mode, a linearly polarized standing wave in a box, and have checked the requirements on it if it's to obey Maxwell's equations. Along the way, we've proposed our two new quantities, P and Q, and have shown that a necessary requirement, given our definitions, is that the quantity Q is oscillating, just like a harmonic oscillator would oscillate. Next, we're going to construct the Hamiltonian for this particular electromagnetic field mode, using these quantities P and Q. Of course, the classical Hamiltonian is just the energy in the field. So our first step is to deduce just what the classical energy would be in this electromagnetic field mode.
Formally, in an electromagnetic field in a vacuum, the energy density, which we could call W here, is 1/2 epsilon naught E squared plus 1/2 1 over mu naught times B squared. That's a standard result in electromagnetism. So that's the amount of energy there is per unit volume. So in a box of length L, then per unit cross-sectional area, the total energy is the classical Hamiltonian, H equal to the integral from 0 to L of this energy density here in the x direction. As I said, this is per unit cross-sectional area, so we're just integrating in this one direction, x. Well, we know what E squared and B squared are from our previous expressions, and those expressions would give us a D squared out front that we can take as a factor, and also we have our half here. And the other parts we are left within our expression are epsilon naught, obviously, times the rest of E squared here, which is P squared times sine squared kx, and 1 over mu naught times the rest of the B squared here, which would give us the C squared, the Q squared, and the cosine squared kx. Well, we can simplify that rather obviously here by using the result that we can relate epsilon naught and mu naught to C squared, so we managed to simplify things a little bit. And we're left with our P squared sine squared kx here, and our Q squared cos squared kx. Well, the integral from 0 to L of sine squared kx is very simple because we know that we fit in an integer number of half waves inside our box. The average value of sine squared then is just a half, and similarly for cos squared. So we get the relatively simple result that our Hamiltonian, the energy per unit cross-sectional area in the field, is given by this expression, d squared L, from our integral of the sine squares and the cosine squares over the thickness of the box, times epsilon naught over 4 times P squared plus Q squared. So with this Hamiltonian we've just deduced here, we're now going to try to choose a value of D so as to get these quantities P and Q to correspond with the analogues of momentum and position with this Hamiltonian. And we will know we've got this right because if we get it right, H and P and Q will obey Hamilton's equations in the form we've seen before, these two equations. Well, the choice that works is to choose D equal to the square root of 2 omega over L epsilon naught, so that therefore our Hamiltonian, which previously we wrote out like this, just becomes omega over 2 times P squared plus Q squared. So if we check out the derivatives here, dH by dP obviously is just omega P, and dH by dQ is just omega Q. But we already deduced that dQ by dt was omega p, and dP by dt was minus omega q. So therefore, with our chosen Hamiltonian function and our P and Q, we do indeed obey Hamilton's equations. Having derived this classical Hamiltonian for an electromagnetic mode, we're now going to proceed to quantize it. As we've proposed, what we're going to do is to substitute the operator P, which we're going to write as minus IH bar d by dq, everywhere we had the scalar quantity p in our classical Hamiltonian. And here was our classical Hamiltonian that we'd worked out. And making this substitution then, putting in this p instead of the classical p, then we obtain the following quantum mechanical now Hamiltonian. It's now an operator with the little hat on it. We've still got our q squared, but instead of the p squared, we've got minus h bar squared d2 by dq squared. For convenience now, we're going to change the dimensionless units. So we'll use xi again as q over the square root of h bar. And for future use, we can also define another dimensionless operator here, a pi operator, which will just be the p operator divided by the square root of h bar. So that would just become minus I d by dxc. So in these dimensionless units, our Hamiltonian then becomes this rather simple form, which is identical to the harmonic oscillator Hamiltonian that we'd worked out before. And we could also write this, because we defined this pi operator here, as h bar omega over 2 times the pi operator squared plus the xi squared.
So now we've managed to follow our supposed procedure for quantizing some classical problems. We started by writing down what we believed would be one example mode of the electromagnetic field, a plane wave in one direction. We checked that what we'd written down was indeed a valid electromagnetic field by checking that it obeyed Maxwell's equations, and we found some conditions as a result. We saw that, at least mathematically, this mode did in some ways behave like a harmonic oscillator. We managed to write down an expression for the energy, the classical Hamiltonian, for this mode of the electromagnetic field in terms of quantities p and q. In doing so, we set the expressions up so that the Hamiltonian and these quantities p and q all obeyed Hamilton's equations. Then we made the key substitution of an operator for the quantity p, by analogy with the momentum operator we already knew. This completes the postulation of the mathematical analogy between a mode of the electromagnetic field and a quantum harmonic oscillator. Obviously, if our postulations here are correct, we should now be able to reuse all of the formalism for the harmonic oscillator to describe the electromagnetic mode, including the raising and lowering operators, or, as we will increasingly call them, the creation and annihilation operators. And that will be the subject of our next section.